Hello. So today we're gonna do a presentation for two papers, which is comparative analysis of search algorithms and introduction to severe weather. We are group 16 or team 16, and my name is Teona Velkoska.
Hi, my name is Dinesh.
Yeah, hi, I am Sai Kumar Gogunene. I am doing my master's in computer science and I came here in this spring 2022. I'm doing a master's here.
So Sai will start the presentation, then I will take over, and in the end, Dinesh will finish it.
Yeah, sure. Thanks, Diana. First, I will cover the topic sets algorithms in AI, and so this is the overview in which these are the key topics that I'm going to cover in here. I'll just introduce about AI, and I'll talk about the sets algorithm approaches that we have in the research paper, and these are the searches. Main problem solving techniques that are used in this paper, like breadth first search, depth first search, uniform cost search, A-star algorithm, and best first search. So I'll compare all of these algorithms and I'll conclude the first paper. So you can go to next slide. So this is the basic introduction to artificial intelligence. Like the main aim of artificial intelligence is like to make humans think like, to make machines think like humans and to perform the tasks like the way we humans are performing. And this is the diagram showing the relation between artificial intelligence, machine learning, and deep learning and data science. So these are all the interrelated topics, and machine learning and deep learning are subtopics of AI, and data science is interlinked to all these topics. So, and in artificial intelligence, we have many things like problem solving. It includes problem solving techniques, many logics like fuzzy logic, and game playing algorithms like min-max algorithm that we have seen in our last paper also, and the probabilities and statistics and Bayesian networks and expert systems, which we have covered in our last paper also. So these are the things that artificial intelligence includes. And there are two approaches that we are using in here, like uninformed search and informed searches. You can go to next slide. Yeah. So these are the two approaches that we are following, like informed search and uninformed search. So in uninformed search, we don't have the knowledge or the proper way, proper direction is not defined in uninformed search. So that's why it is called blind search or brute force search or something like that. But in case of informed search, we have a fair idea of how achieving the goal and we have knowledge about how to achieve the goal state. So that's why it is more efficient compared to uninformed search. And some of the uninformed searches are breadth first search, depth first search, uniform cost search, and bidirectional search. And some of the key informed searches that we have covered in this paper are A-star search and best first search. So I'll going to talk about all these searches in the oncoming slides. So yeah, this is breadth first search. So in this, what we do is we will use FIFO-Q to solve the problem in breadth first search. So if we take 1 as source node, so here the goal state is 8. So our approach should be like going from 1 to 8, and in breadth first search, we will just follow this FIFO mechanism. So from source 1, we have 2, 3, 4 as the open list. So from 2, 3, 4, since we got 2 as first child node, we will add this to the closed list, and after 2 we'll prefer 3 and 4 in the same sequence. So after completing first 3, we will take 6 as goal node, and after that 5. So in the same manner we will reach goal state 8. And some of the main applications in which we use breadth first search are like navigation systems like the GPS, and and our social networking sites. In social networking sites also we use breadth first search, and we may the main problem is like if there is if we don't have any problem about the memory or the storage, then we can go for this breadth first search. And the time complexity and space complexity are mentioned here for this particular search. We can go to next search. So the next one is depth first search. So it is so in this like in the previous one we followed first in first out, but here we follow last in first out mechanism, like we follow in stacks, and so here after considering one as source node, our goal will be reaching the eighth node. So here this depth first search follows ascending order, in which after first after initiating the source node we will go to node 2. After node 2 we will go to after node 2 we will go to 6, and the pattern is given here like in this table 1 2 6 3 5 7. So then the node 2 is enlarged and the child node 2 to 6 is added to the stack using the last in first out method. Then node 6 comes into picture, and then since here node 6 doesn't have any child node, we will go to the we will use backtrack mechanism and we will go to node 4. After that we will come to node 7. Like this way we will reach the goal state 18 here. Yeah, so this is a brief idea about depth first search, and the next search is uniform cost search. So in this uniform cost search, it is it is more efficient compared to depth first search and breadth first search. So as seen in the figure, like it will start from the source node 1, and it will choose the path with the least cost. Like if we start from 1, the from 1 to 2 we have the distance is 2, and from 1 to 5 we have the distance is 1. So the least distance will get closed first. Like in our case, for reaching 5 the cost is 1, so we will go to 5. So 5 will become the closed list first. After that, after completing 5, so if we see it in the figure, node 2 will be completed after completing 5, because the cost for completing so node 2 is also 2 only. And if we compare the same with 9, the distance from 1 to 9 and the distance from 1 to 5, 1 to 2, both are same. The distance is 2 in both cases, but since 2 came first, so here we follow first come first serve. So since we have node 2 first, we will cover the node 2, and after that we will go to node 9. So in the same manner we will go to goal state. Like after 9 we will cover node 3, and nodes since node 3 the distance from 1 to 3 is 3, and after that we will cover 6 and 4, and the distance is same 5 for both 6 and 4. In the same manner we will reach the goal state 13, goal state 12, sorry. And the basic applications for uniform cost search are maze, pathfinding and maze solving. These are the main applications in which we use UCS. Yeah, and this is the equation that we use to calculate this C of m equal to C of n, a function of C of function n and C of n comma m. So in this equation, the cost of previous node is denoted by C of n, and the weight of the each node is each edge is denoted by C of n comma m. And the next search is A star algorithm. So this is a combination of uniform cost search with pure heuristic search. So here we will get function f after combining function c and function of f, function of h. So in the similar manner, we have did in uniform cost search. It will be done in the same manner, but with the help of heuristic search. So the number of steps involved in A-star algorithm also less compared to UCS. So that's why it is considered as most efficient search in the searches that we have discussed till now. And so it is mainly used in designing games and traffic navigation system that we people are following. So this is basic overview of A-star algorithm. And then the next one is best first search or greedy search. So this is combination of breadth first search and depth first search. So it is mainly used in applications like green. It is mainly used in designing games and web crawlers. And after that, if we compare all these search algorithms, I mean, can you go to next slide, Dion? So here is the brief comparison among all these search algorithms. So I mean, to compare all these algorithms, we have to consider four metrics like time complexity, space complexity, optimality, and completeness. So time complexity is nothing but the time taken by the algorithm to discover a solution, and space complexity is nothing but the space required for the algorithm to complete the search. And optimality is ensuring the algorithm solution will always be optimum or not. Like if we are doing this, if we are providing the solution in efficient manner or not, like with less cost and less time. And completeness is whether we are able to complete the given problem by using the algorithm or not. And this completeness will always be a boolean, like true or false or yes or no condition. So so after analyzing all these searches, after carefully analyzing this paper, we will come to the conclusion that heuristic search is mostly efficient comparable when we compare it with uninformed searches or blind searches. So if in UCS, it took 11 steps to expand to the goal state, but in A-star, I mean, it has been decreased to minimal state. So, I mean, with our analysis, we can conclude that heuristic search is more efficient among all the searches that we have discussed. So from here, Tiona will continue on the second paper.
Okay, so I will continue with the second paper, which is severe weather avoidance using informed heuristic search. I will cover the introduction to severe weather, statistics, free flight, Dijkstra method, and method that is Belmont-Ford algorithm, A-search algorithm, and weather damage. And from there on, the last 5, Dinesh will cover it. Let's start with introduction to severe weather. So the severe weather is a big threat, like shows a big threat to safety for any airplanes. The only possible option for this severe weather and is to avoid it. So to choose the road to avoid this thunderstorm. According to that, there has been a new algorithm that finds the shortest path during this thunderstorm, which is A-search algorithm or method. This A-search algorithm is really fast and reliable, and it determines the total path cost of the given point. The evaluation function that gives the estimated cost of the remaining path is basically the summation of the actual path cost and the heuristic function. The heuristic function is basically the summation of the measure of the detour and the addresses that constraints imposed by the desirability of the path. Let's see the statistics here. So there are 21.75% of the aviation accidents in the general aviation that were caused by this bad weather. And also 25.9% of the fatal accidents in the same general aviation that were caused by these thunderstorms. There is a free flight, which is a new system of managing this bad traffic. It provides the pilots more flexibility and also like more control over the road they want to take. And they can decide like with which road to take or whatever when they actually depart the plane. And the free flight option ends with the arrival. But the most important issue in here is that is the safety of the airplane, or we can say that it's not the most desirable road to take sometimes. Let's see the Dijkstra method and the method that is Bellman-Ford algorithm. So we can see, we all know from before, we took like one class with Dijkstra algorithm, and we know that is the shortest path between the starting and the final point. It also has 5 steps. So if we observe the picture on the right side, we can compare it. So first we start with the ending point and we say that we call it our current point. Let's start from 0. So from 0, the second step is we determine the adjacent nodes to that one, which is 1 and 7. Then we compare the weight of the edges, which is 4 and 8. So after that, we choose the minimum weight of the edge, which in this case is 4. So then the next step will be we go to point 1. From there, it comes the third step. So we visit point 1. And then the fourth step, it just covers everything we did before. So we try to find the next closest or adjacent node, which is 7 or 2. And 0 as well, but we already visited 0, so we're just going to continue on 2 or 7 and so on. The last step is when we visit all of the nodes, we stop. Dijkstra method is used in the general aviation for determining the shortest path between 2 points along where the storm can be avoided. But Dijkstra method, on the other side, doesn't promise the most desirable road. Bellman-Ford algorithm is basically focuses on finding the shortest path, and it states the constraints crucial to the road planning for the airplane. These two algorithms are optimization algorithms. Let's see the A-search algorithm. A-search algorithm determines the best part that resolves weather issues. So A-search algorithms is informed heuristic technique, and it has 2 components. The first one is the actual cost of moving from the starting point to the point under consideration. And the second one is the estimated cost of moving from the current point to the final point. The formula for this algorithm is f of n is equal to g of n plus h of n, where f represents the total cost, g is the actual cost, and h is the heuristic function or the estimated cost of the path from node n to the goal state. There are some advantages and also disadvantages to this algorithm. We can say that the biggest advantage is if there is a solution to a problem, or if there is a possible solution, A-search will always find it, and it will not just find just any solution to the problem, but it will find the best solution. But the most popular disadvantage here is that it spent a lot of time, and also it memorizes all the nodes that are visited before, and because of that, sometimes there is not enough memory. Okay. Can go to the next slide. Weather damage. The weather damage or severe weather, it's also called localized storms. The consequences of this severe weather are strong wind shear, or this can damage the structure of the plane. We have violent updrafts and downdrafts, which can significantly change in the altitude of the airplane. And it also makes the pilot lose control over the plane. And we have heavy downpours. So to calculate this algorithm or a search algorithm, we need some data for those calculations. So some of the data are radar reflectivity, which is detecting the intensity of the thunderstorm, wind speed and direction, turbulence, icing severity, and temperature. Okay, so Dinesh will continue. We cannot hear you.
I think you were on mute, Dinesh.
Yeah, sorry, Tim, I was on mute. So yeah, now we understand how these algorithms works and all. So now we'll discuss about how they measure these, paths and the nodes, and what will be the distance between point A to the point B. So here we can see how they calculate the constraints. Basically, they look at the segment length first. It should be a minimum distance. There should be a distance between any 2 points in the flight path to predetermine minimum distance. Then they'll go to turning angles. There are two things to consider here. The turning angle should not be more than 90 degrees and should not be less than 60 degrees. So it should be between 60 and 90 degrees. And they will also look at the number of turns. So how many turns flight is going to take to reach the shortest path with the minimum time. So that's the path they look at, and that will be the end solution for the the algorithm. We'll go to next slide. So here we understand more about thunderstorm avoidance algorithm in real time. Basically, here you can look at the map and understand the trajectory of the plane and the possible paths based on the given starting node and the endpoint node. So they look at the grid size. Based on the grid size, they analyze the actual map size given from the flight radar and the outside trajectory size. If the intensity of these trajectories too high, then that path should not be an ideal path to go forward. And they call it an inaccessible area as well. So because it's the thunderstorm contained area, right? So you should not move the plane in that direction. Then they'll start creating the paths, possible paths to shortest paths, basically, to find to reach the endpoint. Then they'll start defining the nodes from starting point to end point. If you look at the next slide, we'll understand more about how they calculate. So here you can understand the map and the trajectory of the thunderstorm, and point 1 and point 2 as the starting and end point destinations. In the first path, they look at the, if you look at the black line, you can see, the trajectory of the first path. That is the shortest path calculated by A star and some adjacent modifications at SMA star tree. It produced the shortest path within 11.4, and it's the safest path from the a Pentium 2 PC. They use this specific PC to calculate the path. And if you look at the blue line, this is the actual path, which is given when the flight started reaching the endpoint. But because of this thunderstorm in between, they had to calculate the other shortest and the safest path to reach the destination. With the actual path, if you go with that path, it will take the lesser time because that's the shortest path at initial stage before the thunderstorm. So that would given us 11.1 seconds with the same Pentium 2 PC. And the third one, if you look at the third trajectory, it is avoiding everything like thunderstorms, and even they don't care about how many times it's taking. So it's going to be the longest path and also safest path. But the main goal of these algorithms is to find the shortest path to reach the destination. So we'll go with the first line, the black line, because that's the safest and the shortest path. And we'll be reaching the destination within 11.4 seconds. So that's how they calculate, these results. And they use, if you go to the next slide, we can see, how they use these algorithms and all. But there are some limitations to these algorithms. There is some particular standards they follow. If the starting point of the path, lies inside the region, thunderstorm region, they cannot proceed with that path. They have to look for other alternatives. And these algorithms only look at forward direction. They cannot go backward and calculate the path. So there is also a drawback there. And then also, as we were discussing, there are some limitations to the directions, taking turns and all. So the turn should be between 60 degrees and 90 degrees. It cannot exceed or cannot decrease the turning thing. And also there, to conclude this presentation, we can understand how these algorithms produce the results. This A* search algorithm produced the actual results that we needed, and it found the shortest path with the algorithm. They modified some functions, or we can say they enhanced some functions in SMA search to produce this shortest path and reduce the time as well. So these all paths, they'll be in working mode if the all underlying assumptions in a correct way. If algorithm produces safest path, if the given nodes align in a given direction with the path weight. So these are the things they will consider in solving the problems. And I think this A* search tree produced the best results so far to conclude this presentation. And thank you so much, David Knight, for giving us the time to present ourselves and share this information with the team.
And the opportunity to read these papers and
yes,
get upgrade on our knowledge.
Thank you.
Thank you.